Hello, everybody. I hope things are going well for you. And this is a video for lesson number 15. Lesson 15 is about exponential growth. This lesson will be another very important one, and it includes an update concerning the growth of this thing called COVID-19. You may have heard about that. So let's get started. All right, so we are going into a new chapter, which is chapter 6, and this is section 6.1. We will not go into details in chapter 6. We only have a couple of lessons, but the first one is on exponential growth. This is very important because many people think in a linear way, whereas many things in life and in the world grow exponentially. Let me tell you the difference between that, between those two types of growth. So that is the main question. What is the difference between linear and exponential growth? Okay, and so there are two types of growth. One is by a fixed quantity, and this is the one which is referred to as a linear type of growth, right? So we already have an example of this that we have studied, which is simple interest, all right? And so what happens is, as time goes, all right, this quantity, whether it's a number of dollars or the population of a certain country or whatever, if it grows linearly, it grows by a fixed quantity, and that means a number, fixed number, okay? This actually is something that you studied probably like in your high school algebra class, very beginning type of algebra class. It's called the common difference, right? And in algebra, you probably refer to this as the slope. It's the difference of y divided by the difference of x. Now that sounds very algebraic, right? Basically, it goes on a straight line, right? Basically, the rise over run, that's called the slope. And so let me just go ahead and write that, rise over run. And it stays the same. The slope stays the same, and that is the characteristic of that linear growth. And so whenever you have a fixed slope, all right, so maybe the population grows by like 1,000 every year. Maybe the simple interest, you get an interest of $100 every year or whatever, okay? And in that case, you have what is called linear growth. All right, the contrasting with linear growth is this other idea, which is a growth by a fixed ratio. Is there any difference between these two? One grows by constant quantity, the other by constant ratio. The answer is yes, the difference actually is enormous, and that is the point of this lesson. All right, so when the quantity changes with a fixed ratio, that growth is called exponential. All right, so we have also seen an example in the world of finance. As opposed to the simple interest, we had a compound interest, right? And so there is a common ratio, as I mentioned in the previous line, and that rate is called the growth rate. In finance, we call it an APR, the annual percentage rate, right? And the difference is, and so let's say we talked about the compound interest. Later on, we will talk about the musical notes. Of all things, you know, the compound interest is finance. And then we'll be talking about music, which is fine arts. And we will find out that the frequency of these musical notes, you know, like from C to the next C and so on, the frequencies actually grow exponentially. Also, the virus, any sort of a virus spread is going to be exponential if nothing is done, right? So the exponential goes like this. You remember your compound interest? It grows by 10%, say, an year, right? And that's a good compound interest rate, by the way. And then on the $1,000 principal, the first year you get, you know, $100 if it's 10%. But then the 10% of the next or the current balance will be higher than $100 and so on. So it continues to grow like this, right? And that is the difference between linear and exponential growth, all right? Again, the linear refers to growth by a fixed quantity, and exponential refers to growth by a fixed ratio, or percentage. All right, so here are some examples. Let's say town L, this L stands for linear, okay, as opposed to town E, which is of course standing for exponential. All right, so town L is a town where the population now is 10,000. In fact, both of these towns have the current population of 10,000, but it grows by 500 a year. Notice here, this is a fixed number, right? Fixed quantity, not the ratio, but fixed quantity. Now, that's the important part. The way we write this, and you need to learn for your homework and for your exam questions and so on, you have to learn two types of formulas to describe this. Now, formula sounds like maybe a hard word, but it really is just a description in the language of mathematics. So using mathematical notation to describe what happens with these numbers. So just like in the case of a financial calculation, let's say population, the word that starts with P, the current population is denoted with P naught. And so that's the subscript 0. And so let's say P naught is 10,000 because that's what it says here, right? Now, what's going to happen in the following year? Here's what happens, okay? In fact, maybe you can, let's try to figure out what happens to this, right? So P naught is 10,000. And P1, of course, after 1 year, it grows by 500. So it becomes 10,500. And the following year, another 500 is added. So it's 11,000. And then another year, another 500 is added to this number, making this 11,500 and so on, right? And so here's the way we describe this recursively. Recursive means repeated. So P naught is 1,000. Now Pn for the nth number, what do you have to do to get this number based on the previous number? That's the question. And the answer is, because it's growing by a fixed number, you just add, okay, so you take Pn minus 1. This is the, see, this is the current population. This is the previous year's population. And so what all you have to do is to add 500. Okay, so this is the description, which we call a recursive formula. The recursive formula consists of two equations here: the initial value, and then how do you get the nth year population based on the n minus 1th year population. Okay, all this says in human language, English, is take the previous number and add 500. Okay, that's how the recursive formula works. All right, so that's one way to write this, by recursive formula. The other way to write this is more explicit formula. See, the problem with the recursive formula is it's good if you're calculating P naught, P1, P2, P3, and so on. But if I ask you P sub 30, you know, how many people will be in this town 30 years from now? You have to find P30, but to find P30, you have to find P29, which if you want to find P29, you have to know what P28 is, and so on. So it's much better to have an explicit formula for the nth number, right? And so how do you get this number P3? Well, you added 500 3 times. Okay, so that will give you the formula, which is just like the simple interest formula. You start with the initial value, and then it's 500 times n, right? Where this is calculated first. Because if you give them 5 years, okay, so 5 times 500 is 2,500, and that would be the population growth for the 5-year period. So of course, you do the multiplication first in any sort of an operation. You know, if you have addition and multiplication, you do the multiplication part first. And so this is called the explicit formula for the nth year. All right, so for instance, if you want to calculate, maybe I'll use another color here. What happens 50 years from now? Okay, so the answer is, well, you know, you have 500 times 50. You multiply this together because basically this the number increases by 500 every year. And then if you multiply that by 50, and of course this part is 25,000, okay? You add that to the original population of 10,000 and the answer will be 35,000. Okay, so you can say in 50 years, town L will have 35,000 people. Okay, any problems? Great, okay. All right, so now let's go to the exponential town, town E. The population is 10,000, just like this other one, and then growth is 5% a year. Okay, this is very much like simple, compounding interest with an annual compounding of an APR of 5%. Okay, but things are a little different here because well, you know, because you've compared the simple and compound interest before. First year, how do you get the new number? Well, if it's 5% increase, remember what happens? If you add 5% to any number, what you will get is 5% more than the current number, which is 105% of the current number. So you basically multiply this by 1.05. Remember that? And of course, this will be 10,500, just like this number here. So after 1 year, there is no difference between town L and town E, just like there was no difference between simple and compound interest after one compounding period. The difference, however, starts to appear in the second year, right? So now you have this as your P1, and you are going to take 5% more of this, which is to add 5%. What that means is you multiply this again by 1.05. So now you're going to have 1.05 square, right? And then for the third year, you take this 10,000 times 1.05 square and multiply that, or multiply this by 1.05 again. So you'll have 3 of these. Okay, this gives you both the recursive and explicit formula. Let's go ahead and write this down. Okay, and of course, I will give you opportunities to practice this by way of homework. All right, so the initial value, as before, is 10,000. All right, and then how do you get the nth year population, the population after n years? Well, you take the previous year's population, which we denote as P sub n minus 1, right? And then what do you do with this? You take the previous year's population and multiply that by 1.05. Okay, so that's how you can write the recursive formula. The recursive formula always has 2 parts. First one is the initial value or the initial quantity, and then the other one is Pn is equal to, and then this will be an expression using P sub n minus 1. Because the question here is, how do you get the next value based on the present value? Okay, the explicit formula is the one that will get you directly to the nth year population. Right? You see what's going on here? If P3 is 10,000 times 1.05 to the third, and then P4 is going to be 10,000 times 1.05 to the fourth power. Okay, I think it's easy for you to see that after n years, all you have to do is really to take that 1.05 to the nth power. Of course, you do this first because the exponential operation precedes the multiplication operation. And you can put times here if you like. Okay, this is how you can find the population n years from now. Okay, make sure you do this first. All right, so I hope you can see the difference. All right, and so you can calculate, for instance, the 50th year, the population 50 years from now. And so that would be 10,000 times 1.05 to the 50th, right? And you can take your calculator and calculate this, or you can sort of guesstimate, you know, is this going to be more than 35,000? I hope you remember from the compound interest that when you save money, the compound interest or the power of compounding works for you. So the answer will be more than 35,000. How much more is the question? So take your calculator and see if you can do this first. Again, make sure you do this one first, okay? Maybe I can show you how to do that. Okay, so here's a calculator, and this is something I just pulled out of the Microsoft operating system. I think I have the Windows 10, but you should be able to find the scientific calculator on your PC or device you use. All right, so what I'm supposed to do is 1.05, okay? And remember how you raise any number to a power? you do this x to the y on the calculator. Sometimes it's the caret notation. And then you raise it to the 50th, 5, 0, and then you put equal. All right, so this is 11.46 something. That is the 1.05 to the 50th power. All right, and then you just multiply this by, where is the multiplication? Right here, by 10,000. Okay, you see 10,000 right here. Right, and the answer is going to be 114,673.99. Let's round this to the nearest number because we are talking about the number of people, and certainly you should not have fractions of a person. All right, so if you just write this down, what we found is this part was 11.467 something, and multiplying that by 10,000, you get 114,674 after rounding up. Okay, what was the linear growth? After 50 years, you'll have 35,000. With the exponential growth, where even the first year, it's the same 5% growth, but in the linear growth model, remember, it was a 500 people every year as opposed to 5% every year. And notice the difference. I mean, notice the vastness of the difference between linear growth and exponential growth. See, we tend to think linearly, like, oh yeah, it's 500 people this past year, another 500 next year, another 500 the following year. That's linear thinking. And that is dangerous because in reality, most things, if nothing prohibits the growth, nothing stops the growth, nothing, no, it's not prohibit, nothing inhibits or slows down the process, most things in life or the world grows exponentially, including the population of species, populations of animals, populations of viruses, populations of all kinds of things. Even the temperature worldwide seems to be growing exponentially. And that is very serious, right? If you think about this. All right, so instead of 35,000, you get like 3 times as much, even more than triple the amount after 50 years. You'll end up with 114,000 people in this town E as opposed to town L. All right, I don't know if you can see this, but in red, we have the linear growth. That's straight line, okay? And in fact, that's where the word linear comes from. You see the word line right there, right? And this is yellow. It's hard to see maybe on your screen, but this is your exponential growth. And this is showing you the population of town E. You see that about 50 years, the difference is between 35,000 and 114,000. And you can see the clear difference between those two. And it is very important for you to distinguish linear and exponential growth. All right, let's go to the next page, and I will pause this this video for this part, and we'll go into part 2.